And record. All right, so we've pointed a lot at the periodic table so far this unit, right? But we haven't formally introduced it. So this, yes, is a picture of the periodic table, right? So we need to introduce ourselves to a couple of terms. So this first term, periodic law. Periodic law is sometimes referred to as periodicity. Periodicity. Okay, and so what that means is that the properties of elements vary in a periodic way. And periodic way, what we refer to is repeating. They vary in a repeating manner. So let me explain what I mean. When I look at the periodic table, the reason why the periodic table is built the way it is for a couple of reasons. We've already mentioned that the atomic number goes up from left to right, and then you get to a new row, and then the atomic number continues to go up. So atomic numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. And now you guys know that the reason why there's these shapes and columns is because the electrons in these elements, they fill in certain subshells, and they have to fill in a certain order. 1s fills first, and then 2s, then 2p, then 3s, then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, and so on. So those patterns hopefully are starting to sink in, and they're starting to make sense when you cross-reference this with the arrow diagram. But the term periodicity comes about because if I were to pick any one of these, oh, by the way, these are rows. These periods are rows. And so there's 7 periods. Period 1, 2, 3, 4, 5, 6, 7. The period is essentially the energy level. Which is also a row on the periodic table. Okay, so if I were to look at one period right here, let's look at period 2. The elements in period 2 are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, so when I go from left to right, here's what I observe. Lithium reacts very easily with water. Okay, beryllium, yeah, it reacts with water. Not as much as lithium, but it still reacts. Boron, not so much. Carbon, not so much. Nitrogen starts to react with water again, and so does oxygen, so does fluorine. And then you get to neon, which does not react with anything. Okay, neon is element number 10. If I were to continue to the next period, that brings me to sodium, which is element number 11. And here's what sodium does. Reacts a lot with water. Magnesium reacts somewhat with water. Aluminum, nothing. Silicon, nothing. Phosphorus starts to. Sulfur does a little bit more. Chlorine really does, but then argon does nothing at all. If I continue on to the next row, that same pattern that I just described is going to happen again. And if I move on to the next row, that same pattern is going to happen again and again and again. The fact that we have repeating patterns over and over and over again, that is the concept of periodicity. Okay, so the properties vary in a repeating way. Okay, so if a period is a horizontal row, then you need to know that the vertical columns are called groups or families. And there's 17 of them. 17 columns. If we wanted to number them, we could. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18. Okay, so did I say 17? I meant 18. Technically, there are more columns if you count these guys here, the Fs, but we're not going to count them because they're not what we encounter every day. There are 4 families, 4 columns that you will need to know the names of, and they are here. The first column is called the alkaline metals. Okay, now while I say that's my first column, I'm going to point out that hydrogen is not. It's not a metal. So we kind of ignore hydrogen. We don't call that part of the alkaline metals, but everything below that, lithium, sodium, potassium, rubidium, cesium, francium. Okay, those are all alkaline metals. Now, I'm not going to ask you to recite what the alkaline metals are, but if I point to one of them and ask, what family is this in? If I said, what family is potassium? Yes, you should know that that's an alkaline metal. Okay. The second family that you need to memorize is what we call the alkaline earth metals. Alkaline earth metals. The second column. Beryllium, magnesium, calcium, strontium, barium, radium. Okay, so far the first 2 columns. Then jump all the way over to the far right. The last column, the noble gases. We've already talked about them a little bit. We've been using them for our bookends when we use our shorthand notation. Okay, so the noble gases, you should know that the noble gases don't react with anything. That's why they're called noble, because they don't mix. Back in the day, when they were first studying chemistry and there were king's courts and royal courts are not allowed to mix with commoners, like the king, the queen, the bishop. Like if you think of British royalty, like Queen Elizabeth, right? They don't just go walking down the street hanging out with the general citizens, right? They don't do that. They're not allowed to do that. They have to keep themselves separated, right? Noble gases, they don't mix, which means they don't react. Okay? And then the second to last column is called the halogens. You might have heard this term because of a halogen light, right? Fluorine, chlorine, bromine, iodine, astatine. Okay. Then the valley here, the middle D block, has another name. Instead of calling it D block, they are called the transition metals. Transition metals. And so the bottom guys down here, right? The guys we know as the F block. The F block is made up of 2 rows. The first row is called the lanthanides, and the second row is called the actinides. And the reason why they have those funny names is if you look closely, cerium here, the first element in the lanthanides, follows the element lanthanum. Because if you follow the fill order, this comes right after this guy. This thorium comes right after this guy. That's why this whole row here is called the actinides, because they follow actinium. All right? Lanthanides, actinides, that name in and of itself is not that important, but you should know that the F block is also referred to as the inner transition metals. So you got transition metals, but then you got inner transition metals. Why are they called the inner transition metals? Because they need to be put back in the periodic table. They've been removed, but really they belong here. Okay? All right. Periodic table, 4 main families you got to know, and a couple other parts. Transition, inner transition. So far, so good? Okay. So let's take a look at, let's see, I need a bolder pen for this. Oh, that's probably too big. We'll go this way. Okay, so there is a separation line on the periodic table that looks like a staircase. It's not showing up on here, but if you look at the one up above me, see that bold line? Okay, that's the staircase, and that's important because that separates the metals from the non-metals. Okay, so metals are located on the left side of the table, meaning the left side of the staircase. All right, so all of these guys here all of these are metals. So what that means then is you've got a small portion of the elements of the periodic table, which are called nonmetals. Now you, from your life experience, have encountered metals. You know what metals are, right? They're hard, they're shiny, they can bend, they conduct electricity. All of these properties of metals, right, you have some familiarity with. The term malleable means that they can be shaped with like a mallet. A mallet is a British word for hammer because blacksmiths used to take metals and form them into the horseshoe shapes for their horses. That's where the term comes from. Okay, it just means that the metals can be shaped. Ductile means that you can pull on it until it's so skinny that it becomes a wire. Metals can make wire. Luster means that they are shiny. Something with a luster is shiny. And then they conduct heat, also electricity. And they are mostly solids at room temperature. There's one metal that is not a solid at room temperature. Anybody know what it is? Mercury, right. You put it in thermometers. Thermometers with mercury used to be very common. In fact, when I started teaching here, we had thermometers that were mercury thermometers. And then eventually they got to the point where they thought, okay, it's really hard to clean these up safely because if you break a mercury thermometer, the mercury spreads out and the drops of mercury fall and make pinging sounds when they hit the floor, like these little beads, and they fall and they bounce all over the floor, and the vapors that come from the mercury liquid are toxic. So if we broke a mercury thermometer, we would have to like clear out the room, and we'd have to come in here with like a special dust which reacts with the mercury and turns it into like a sludge kind of, so it can be wiped up, because otherwise it's just like this bouncing metal ball all over the floor. It's really hard to deal with. So anyways, so those are the properties of metals. Okay, so then on your periodic table, like easily like 80% of your periodic table are metals. So your nonmetals though, what are those properties? Well, they're kind of exactly the opposite of metals. Right, so they're not ductile, so you can't make wires out of them. They're not shiny. They don't conduct electricity. Most of them are gases. Some are solids. Most of them are gases at room temperature. And they're located to the right of the staircase. Now, on the periodic table, above me or to the left or to the right, do you see how the elements are color-coded? How there's black, red, or blue elements? Okay, so the black is solid. At room temperature, any element that's written in black ink is a solid. Anything that's written in red is a gas. And there's two blue elements. We already mentioned one of them. Hg is mercury. What's the other one? Br. Br is bromine. Bromine is a nonmetal, and at room temperature, it's a liquid. Okay, so, just not a lot of liquid elements at room temperature. You can get more at higher temperatures, right? But you'd have to heat up everything. Okay, so we have two types of elements, metals, nonmetals. And then we have a third type, which we call metalloids. The in-betweens, they're semi-metals. And semi-metals have properties of both. All right? So where are these semi-metals? They are on the staircase line. They're the ones touching the staircase. Okay? Except for aluminum, right? So not aluminum, but everything else here that's touching the stairs, either above it or below it, is a semi-metal. There is one semi-metal on here that is the most important economically than any others. What do you think it is? It's the most used today. Silicon. Yeah, silicon. What do we use silicon for? Yeah, computer chips, microchips, right? Not silicone. Right? That's something different altogether, right? Silicon. Silicone is a compound that might contain silicon. But, okay. So right now there's a shortage of facilities that can manufacture microchips, and that's why buying electronics today is very hard, right? Everything's expensive. Everything's in short supply. Okay. So if we pick a family on the periodic table, like this first family with sodium, potassium, rubidium, I picked these families. What family are these guys from? Alkaline metals, that's right. These are the alkaline metals. Now, if I wrote out the electron configuration for all of them, sodium ends in 3s1, potassium ends in 4s1, rubidium ends in 5s1. Cesium ends in 6s1. They all end the same way, and they're all going, everything in the same family ends the same way. Okay? They have more electrons or less electrons, but they always end the same way. So that's important. This is, again, related to periodicity, the fact that if they're in the same column, they'll do the same thing. They'll behave the same way. The fact that these have the same number of electrons, or I'm sorry, the same ending, same number of outside electrons, what that means is these elements will react similarly because of this, this, and this. There's a term for these electrons, the outermost electrons. They are called valence electrons. The valence electrons are defined as the outermost electrons, or the electrons in the highest energy level. What do I mean by highest energy level? I mean, if you wrote out the SPDF notation, literally, what is the highest energy level you see? In this one, it's 3. In this one, it's 4. In this one, it's 5. So whatever electrons are in the highest energy level number, those are valence electrons. And valence electrons are important because valence electrons are the only electrons that can interact with other elements. They are the important electrons. There's lots of electrons in any given element, but the only ones that will do anything are the ones on the outside. So, if those are called valence electrons, let's highlight this with pink, valence electrons. The other term you need to know is what we call core electrons. And core electrons are the rest of the electrons that are underneath. So these guys here in the blue box, those are the core electrons. But the pink highlighted, these are the valence electrons. All right, so in any given SPDF notation, you need to be able to identify the core electrons. You need to be able to identify the valence electrons. So here in silicon, take a look here at this example. How many valence electrons do you see? So you have to be careful. Find the highest energy level, which is what? 3, and 3 is actually in 2 places here, right? So the valence electrons are what's found in 3s and in 3p. So these guys here are the valence, and then the rest are the core.
Wait, why adding 2 valence?
Because the valence electrons is defined as the electrons in the highest energy level. Because S and P are both in 3, energy level 3. Yeah. Okay, so arsenic. So if I write, let's just do the shorthand for arsenic. Arsenic starts with argon. Okay, so argon is 3p6, which means it follows by 4s. And arsenic has 33 electrons. So 18, so 4s2, 3d10, and then 4p3. Okay, so that's the shorthand SPF notation. What is the highest energy level you see? 4. So that means this and this means that there's 5 valence electrons. The 2 in the S and the 3 in the P. So if those are the valence electrons, the rest, these plus these, are not valence electrons, so those would be called the core. So how many core electrons are there in arsenic? 28. There are 28 because you have the argon plus the D. So 18 plus 10, 28. This making sense? Okay, let's try another one. Let's try barium. So barium is xenon. So barium has 56 electrons. Xenon represents 54 of them, and xenon is position 5p6. So according to our fill chart, what comes after 5p6 is 6s2. And that's it. I'm done. Okay, well this one, there's not a whole lot of writing. How many valence electrons are there? 2. How many core electrons are there? Right. Take a second. I want you to see if you can figure out I, core electrons and valence electrons. I is iodine, element 53. So who's got a guess? How many valence electrons are in iodine? Jason? 7, good. Okay, so let's write this out. We start with krypton. Krypton is position 4p6, which means we start here with 5s2, After 5s2 comes 4d10. And I have to work my way up to 53. So 36 plus 2 is 38, plus 10 is 48. So I got 5 more to go. So next, after 4d comes 5p. That's going to be 5p5. All right, so that is 53 electrons. The highest energy level shown is 5. And so when you add those two together, that's 7 valence electrons. And so since we know the valence electrons, we can go ahead and add the core, and we see that there are 46 core electrons. Okay. Let's do the last one here, lead. This will be the last one, and then we'll stop here. So try to figure out lead. How many valence electrons does lead have? Lead is element 82. This one involves a little more work, even if it's shorthand. Do we have any guesses? How many valence electrons are we talking about here? Yeah.
4.
Yeah, good, 4. Okay, so after 5p6 comes 6s2. Then if you're following a fill order, you remember you have to go to 4f next. So that's 4f14. And then after that comes 5d10. And then comes 6p2. So for valence electrons, the highest energy level shown is 6, which means 4 valence electrons. And then the rest would be core. How are we doing?
Good.
Good? All right. So now after having gone through all of that, I just want to show you a little time-saving technique. If we look at the periodic table, which is a bit of a mess here because lots of writing. Did you notice that in all of our examples, our valence electrons, the highest energy level always was either in the S or the S and Ps? Did you notice that we never circled the Ds or Fs when it came to valence electrons? And that's because of fill order. Right? The highest energy level is always either going to be the S or the P electrons. So what that means is you can predict very quickly and easily the valence electrons simply by looking at the periodic table. If it's in the first column, these guys are all going to be S1s, which means they have 1 valence electron. If they're in the second column, they're all going to be S2s, which means they have 2 valence electrons. We're going to jump over the Ds. We're going to come over here. If it's in the first P column, these guys will all be S2P1s, which means they have 3. These guys here will all be S2P2s, which means they have a total of 4. These guys here have a total of 5. The 6th column has 6. The 7th column has 7. And the 8th column has 8. Because we never count the Ds and Fs for valence electrons, because those are just not and a high enough energy level, the valence electrons will always be simply found by whatever column it's in. So, phosphorus, how many valence electrons? 5. Calcium, how many valence electrons? 2. Chlorine, how many? 7. Xenon, 8. Tin, lead, germanium, silicon, carbon. You guys get it? Okay, it's a little time saver. Okay, that's a good enough start here.